So now let's prove that for the sequence a sub n equals 1 over 2 to the n, that this really is satisfied, and then we'll talk a little bit about why this is a good thing to know about that sequence and why it really encapsulates the statement the limit is equal to 0. Okay, so we want to show that for every possible error tolerance, there's some waiting time such that any time after the waiting time, we're going to be within the desired error tolerance of our desired limit. Okay, and again, you can think about these bars, and the idea is that anybody can specify those bars to any super narrow width, as long as it's not 0, and we'll be able to get in there and stay there. So, I do think I need to erase that. Okay, so the claim is that the limit, specifically of 1 over 2 to the n, is equal to 0. Okay, this is pretty easy because it's such a simple formula. And the way you would start a proof like this is always the same way. Very often when you're asked to prove something in mathematics, the statement you're trying to prove starts out for every such and such something is true, because those tend to be the most interesting and powerful statements. That they're universal, at least to some degree. And the way you always start that is you've got to say, okay, suppose I'm looking at a certain value of whatever this quantity is that's supposed to always work. Let's show it works for that value. And the way you usually do that is you start with the word let. And you say let epsilon be some real number, some error tolerance. Oh, and let's remind ourselves that we don't need to satisfy negative epsilons or 0. That doesn't make any sense. Okay, so we just say let epsilon be greater than 0. So that's really saying we're going to show no matter what that epsilon is, that we can make this work. And that's how to prove for every epsilon greater than 0, this statement is true. So, if you start a proof, let is a pretty good word as a guess for what the first one is, for the first word. Okay, let epsilon greater than 0. Okay. So we need, let me just put in parentheses, we need the waiting time n. Okay. And what do we need to know? This is something you don't absolutely have to write in the proof, but it comes into the thought process of figuring out the proof. We need n such that when n is greater than n, 1 over 2 to the n is less than epsilon. Okay. Well, you know what? Why don't we just make sure that when n is equal to n, it's going to be less than epsilon. And then we know that these guys are getting smaller as they go. One of the nice things about this is it doesn't bump up and down in a weird way that would make it hard to satisfy the whole and stays there part. So let's just be a little bit more ambitious, and let's just say, let's find an n, and this is often what you do, such that 1 over 2 to the n is less than epsilon. Okay. Then certainly, if little n is bigger than that waiting time, if it's actually gone past the boundary, the waiting time, then we're going to be golden. Okay. Well, all right. So let's just say, what if it was like approximately equal to epsilon, or even equal? We're just playing with it right now. We're figuring out the proof, not writing the formalized details. Oh, that's an equation we can solve using logs. Okay. So that's 2 to the minus n equals epsilon, and minus n is log base 2 of epsilon, or n is minus log base 2 of epsilon. Now, we changed like a less than to an approximately to an equals, so we got to fix that. In particular, n is supposed to be an integer. I'm not allowed to put in anything but integers into the sequence, and traditionally n should be an integer to not overcomplicate things. What if I pick some epsilon, like for example 1/10 or 1/100th? That's not a power of 2. The log 2 is not going to be an integer, and so minus log 2 epsilon is not going to be an integer. But remember, this is the great thing about this whole process, is there's a lot of wiggle room. We just needed some waiting time such that eventually after that it's going to work. We can always like take 1 plus things, or if this isn't an integer, just bulk it up a little bit so that it is an integer, and we're good. Okay, and there's a nice notation for that. So we're going to say, let's take minus log 2 epsilon. You're thinking of epsilon as a small number, like 1 over 100, 1 over 1,000, 1 over a million. That's where it gets interesting. That's where it gets hard to satisfy this. The log base 2 of a really small positive number is a big negative number. The negative makes it a big number, which makes sense. We expect to have to wait a while. Okay, but it might not be an integer. Well, let's just take what's called the ceiling of that. And these little brackets, kind of half square brackets with just the ceiling part, is a nice notation for that. And it just means the smallest integer greater than whatever this funky number is minus log 2 epsilon. Okay, so now, and it's fine, when you're writing down a proof, it's totally fine, I think, as a teacher, to write, as long as you're clearly saying, hey, here's my thought process, to write all this stuff out. But when you see proofs written out, unfortunately, they tend to take that stuff out because they want to look really, really elegant and clever, and it can be really a mystery, like, how did they get that? Okay. So then we're just going to let n be this magic number. Okay, minus log. So take that epsilon, take that error bound or tolerance or whatever, do this calculation to it. That's going to produce some positive number, and then just make sure you go a tiny bit beyond that, and that's our desired waiting time. Then, let's see, okay, if n is greater than n, then n is certainly greater than minus log 2 epsilon. So log 2 epsilon, let me just switch it around, is less than minus n. And then, oh, hey, guess what? If I then see what's true about epsilon, then epsilon is less than, let's see. Greater than, there we go. So I switched the order of it, but I also multiplied by a minus sign, so I just forgot. Aha. So log 2 epsilon is greater than minus n. That's pretty important. Now, I switched that to a statement about powers. So epsilon is going to be greater than 2 to the minus n. Or in other words, 2 to the minus n, which is the value of a sub n, is less than epsilon. And we already know none of these are ever less than 0. So this wasn't something we were worried about. It goes too low than the limit. And often that's quite possible. But here it's a little simpler. So a sub n is positive, and it's certainly less than epsilon. And the reason it is we were clever enough, using some logs, to choose the waiting time big enough so that this is going to work. And that was because we chose a waiting time so that this was going to work. So you just basically say, okay, express epsilon as a power of 2, or close enough, and fudge it a little bit up in case it's not exactly, which it probably won't be. Then wait that many powers of 2, maybe a little more if you need to, but this works here. And when you wait that many powers of 2, you're going to be good. So for example, with 1 over 100, let's get really explicit. With 1 over 100, this minus log 2 epsilon is going to be between 6 and 7, because this is between 2 to the minus 6 and 2 to the minus 7. So that's going to be, this is going to be between 6 and 7. Taking that ceiling goes ahead and says, well, let's do 7 to be safe. And then as long as n is greater than 7, you're totally fine. In fact, that actually is a tiny bit more than we really needed, because then that's just saying if it works for 8, 9, 10, etc. And it totally works. By the time you get up to 8, 9, 10, 2 to the minus 8, 2 to the minus 9, 2 to the minus 10, definitely within minus 1/100th and 1/100th. In fact, here it's between 0 and 1/100th, because these guys were obviously positive. So this is an example of how you would prove that explicitly. Let me talk about what's really crucial here as a takeaway and what's not so crucial. You might think, oh man, every time I have to analyze the sequence, I have to do this minus log 2, I have to do the ceiling, all that kind of stuff. The exact point of this definition, and a lot of definitions like this, is that when you open up the guts of the thing, and you prove this once, you might have to do a finicky calculation or some kind of complicated argument to say, yes, there is an n, I can calculate it, or I can show that it exists in some more abstract way. In other words, given a certain error tolerance, I really temporarily think hard about just how long do I have to wait to get into that error tolerance. Here, it has to do with log base 2 of what the error tolerance is. But the point is, this is the only time you ever do this. Then, what does the definition say? Right? The definition says, to say this, let's write it out again, given any error tolerance I can imagine, there is some n. You often just say greater than 0, and it's understood because it's called n, that it's an integer, okay, such that if the actual index you're going to put in is after the waiting time, the terms compared to the distance between the actual terms and the putative limit is less than that epsilon. Okay. This definition doesn't require you to really ever to say, oh, and by the way, the formula for big N in terms of epsilon is something in terms of logs. It just says there is one. It says that no matter what customer I have, I'm trying to serve, no matter how finicky that person is, there's some waiting time after which they're good. And so it's very, very important. There's a very big difference between the somewhat grungy mechanism of sometimes proving these limits exist or equal to a certain value for some particular sequence, and then what you get out of that. All of that sort of sausage that we were making with the log2s gets hidden in this definition, and just in this notation. It says, yeah, these guys get as small as you want eventually. And for a lot of things, that's all you care about. You don't really need to unpack and say, oh, well, my tolerance is 1/1,000,000th. How long do I have to wait? The mathematician says, that's unnecessarily finicky. We told you you're going to be able to do it. If you really, really care, if you really, really care about n, then you are going to have to unpack that definition and go back and say, oh, what is the relationship between the error tolerance and the needed waiting time? But for an amazing number of things, you can prove a lot of wonderful things about limits and derivatives and integrals just knowing that there is some waiting time and knowing that somebody else who you trust found some actual maybe more or less explicit version of it, like with the log2s, but you don't care. So I think sometimes students, when they are exposed to like these epsilons and things like that, they think, oh my God, this is so hard. You're making it so hard. But it's only if you actually really have to be that one person in the history of humanity who actually sits down and proves it and does the careful analysis. And then they just pass it on in this form, and nobody else actually has to worry about the details. So let's, this is getting a little long, but let's do one more example. Remember S sub n? I haven't been paying a lot of attention to that. That was the sum, 1 plus 1/2 plus 1/4, all the way up to 1/2 to the n. Or if you want summation notation, let's have it like a dummy variable, k equals 1 to n of 1/2 to the k. If you don't like summation notation, you can always just think of it as this. Okay. And our claim for that is that the limit as n goes to infinity of S sub n was equal to, oh, it was just 1/2, sorry. Sometimes people started with 1, I've talked about that, the sum is equal to 1. Okay. Or, in other words, and you'll see this very often with summations, when you combine the notion of a limit as the number of terms goes to infinity of a summation, this is known as the infinite sum. Really, really important that when you put this symbol with the summation, or you could say 1/2 plus 1/4 plus, and then you just don't put anything after the dots. Really, really important that when you put this infinity in there, there is an implied limit. Absolutely. That the definition of this is you look at the sequence of partial sums, and then you take a limit of that sequence, and you're asserting that that limit is equal to 1. Many, many people get confused saying, oh, I stick infinity into it, or I literally add an infinite number of things together in some magical way. That's not what you do. And we make an end run around the fact that you can't really operationally add an infinite number of things together. You define it as a limit of a trend of a sequence of finite sums. Okay, so at the risk of going a bit long, pause it, get a little cup of coffee, a little drink, a little snack, something like that. The key here is that there's a much better way to write that formula. Okay. We actually have, you should have a really good guess, because we know what the answers are. It's 1/2, 3/4, 7/8, 15/16. And just from the picture, right at the first video, I noticed that everybody is a certain distance away from 1. This is equal to 1 minus 1/2. This is 1 minus 1/4. This is 1 minus 1/8. This is 1 minus 1/16. Oh my God, that's really simple. Given that I already analyzed the 1/overs, 1 minus 1/32. Oh gosh, okay. So this number, even though it was created out of a sum of a bunch of guys, there's a huge shortcut even at the level of just the finite terms here, which is this is just 1 minus 1/, whatever the last power of this guy was, which was just 2 to the n. Okay. Alrighty. So now the claim is that the limit of S sub n is equal to 1. Okay. Now there's two ways to do that. Okay, and so these guys are going up, 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 but I'm not going to waste the space on it. Okay. The hard way, good for practice, is to say let epsilon greater than 0. And then you use exactly the same n here because it's a very simple modification secretly of the sequence we were already doing. Let n again be the ceiling of minus log 2 epsilon. Basically express epsilon roughly as a power of 2. Make sure you overestimate a negative power of 2, overestimate whatever the negative power was. Then, if little n is bigger than n, then 1 minus 1 over 2 to the n, what are we trying to show? We're trying to say that guy, the distance between that and 1, ha! The 1's cancel, and inside an absolute value, the minus goes away. Ha! Look, that's exactly what we were talking about before. Okay, that is definitely verbatim the argument we had before. That is less than epsilon. Okay, and we're done. Now, that was actually the hard way, because we're kind of reproving almost and using the nitty-gritty details of a previous proof. And you shouldn't really have to do that too often. I promise I'll end after this one, but another video we'll do some other cool examples. The easy way is first, I guess it's the easy way because first you do some hard work to prove a general result, and then you take advantage of that. First you show that, for example, the limit of a sum or difference is the sum or difference of limits. Or you trust that, like, the book is going to have a proof, it's going to have this, or at least a statement of this theorem in any kind of calculus book. And then you just say, oh, the limit, I don't know why I capitalized that, the limit as n goes to infinity of 1 minus 1 over 2 to the n is the limit of a constant sequence, well, that's definitely going to be simple, minus the limit of the sequence we just did, and that's 1 minus 0, and that's 1. There, I didn't have to go back into the whole log 2 epsilon thing, and that's really important. And this is a good example of once somebody else did that nitty-gritty for one of these sequences, then you can leverage that and use that and say, oh, a lot of things based on this, I don't have to ever do that calculation again. I just prove general results like this, which you have to do a little epsilons and n's for that, and then you can manipulate them as long as you're careful. And that is important. Okay, great place to stop this one.